Welcome back. Let's define the double integral of a function f over a rectangle R for one last time. So let's say that R is a rectangle which is determined by the interval from a to b along the x-axis and the interval from c to d along the y-axis. To define the double integral of a function f over this rectangle, we are going to divide this rectangle into m vertical strips and n horizontal strips here, and then as a result of that we get m times n subrectangles. The let's say that this green subrectangle is the ijth subrectangle, so I'm calling that Rij. In this subrectangle we are picking a test point, xij star comma yij star. We evaluate the function f. We evaluate the function f at this test point, and then we multiply by the area of this subrectangle, delta aij, and then we sum over all these subrectangles. So we get the summation I going from 1 to m, summation j going from 1 to n, f of xij star comma yij star multiplied by delta aij. Now this sum here is the Riemann sum of f with respect to this Riemann sum of f with respect to this partition here of the rectangle R. And so this is the Riemann sum, and then we take the limit as mn goes to infinity. That's the double integral of f over the rectangle R. So now let's say that we are looking at the double integral of the function 6x minus 4y squared over the rectangle R, where R is given by the interval from 0 to 2 along the x-axis and the interval from 1 to 3 along the y-axis. So here is this rectangle R. And I'm going to estimate this double integral by using Riemann sum. So I'm basically going to divide this rectangle into 4 pieces. So I'm dividing it right along where x is 1 and right along where y is 2. So we get these 4 subrectangles. And in each of these subrectangles, I'm going to pick the midpoint. Okay, so let's look at this first subrectangle here. So the midpoint that I picked here is the point where x is half and y is 3/2. So I evaluate f at half comma 3/2, and I multiply by the area of this subrectangle. Now the area of this subrectangle is 1 because it has length and width equal to 1. And now if I look at this subrectangle here, the midpoint here is 3/2 comma 3/2. So I evaluate f at this point, multiply by the area of that subrectangle, and I do the same thing with in this subrectangle. The midpoint is half and 5/2 here. So this is 5/2. So f of half 5/2 times the area of this subrectangle is 1, and the last one is this midpoint here is 3/2 and 5/2. So f of 3/2 comma 5/2 multiplied by 1. So now we just evaluate the function at these points. So f of half comma 3/2. So if I replace x by half, y by 3/2 here, then we end up with 3 minus 9. If we replace x and y by 3/2 and 3/2 here, then we are going to get 9 minus 9. Replacing x and y by half 5/2 here will give us 3 minus 25, and f of 3/2 comma 5/2 would be 9 minus 25. And then we just do the arithmetic here, and at the end we get negative 44. So that is our estimate of this double integral. Of course, this is probably not a good estimate, but if we divide this rectangle into more subrectangles, we'll get a better approximation of the double integral. Okay, so now I want to present the conditions for the double integral of the function f to exist. So what are the conditions that will guarantee the existence of the double integral of f over the rectangle R? Well, if f is a continuous function on the closed rectangle R, then the double integral of f over R will exist. And a little bit more general theorem is that if f is a bounded function on the rectangle R, and if the set of discontinuities of f on R has zero area, then the double integral of f over R exists. Okay. So these two theorems tells us under what conditions the double integral exists. Now, some properties of the double integral are the following. Let's say that f and g are integrable on the closed rectangle R, and let c be a constant. Then the double integral of f plus g over R is the same as the double integral of f over R plus the double integral of g over R. So number one is telling us that we can take the double integral of a sum term by term. The double integral of c times f is the same as c times the double integral of f. So if I have a constant factor in my integrand, that can be taken outside of the integral. If f of xy is less than g of xy for all xy in the rectangle R, then the integral of f is less than the integral of g. And if if the absolute value of f is also integrable on the rectangle R, then the double integral of f over R, the absolute value of the double integral of f over R is less than the double integral of the absolute value of f over R. Okay, so those are the four basic properties of the double integral over rectangles. Here is Fubini's theorem, and it's what it allows us to do is express the double integral in terms of iterated single integrals. So if f of xy is continuous on the rectangle R, then the double integral over R of f of xy exists, and the double integral can be expressed as this iterated integral where we have the integral from a to b, integral from c to d, f of xy dy dx, which the meaning of this iterated integral here is that we take the integral of f with respect to y first, and then once we compute this integral with respect to y, then this inner integral is going to give us a function of x only, and then we can integrate that with respect to x. So we can write this double integral as this iterated integral here. We can also write the double integral as the iterated integral where we integrate with respect to x first, and then we integrate with respect to y. So here we compute the inner integral first. Once we compute this, we're going to get a function of y, and then we calculate the integral with respect to y. Keep in mind that when we are integrating with respect to y first here, we're going to assume that x is fixed. Similarly, when we compute the integral with respect to x first, we're going to assume that y is fixed. So let's do an example to illustrate this Fubini's theorem. Let's say we want to find the double integral over r of 6x minus 4y squared. Here r is the rectangle given by these two intervals here. So this is by Fubini's theorem. X is going from 0 to 2, y is going from 1 to 3 of 6x minus 4y squared dy dx. So we decided to integrate with respect to y first, and then we're going to integrate with respect to x. Now with respect to y, what's the antiderivative of 6x? Well, 6x is a constant, so with respect to y, so the integral of 6x would be 6xy, and the integral of 4y squared with respect to y would be 4y cubed over 3. And then we have to evaluate this antiderivative at 3 and 1 and subtract. So we plug in 3, we get 18x minus plug in 3 here, that's going to give us 4/3 9 cubed, so that's going to give us 36. Plug in, if we plug in 1 here, then we get, remember we're plugging in y equal to 1 here, so we get 6x, y equals to 1 here is going to give us 4/3. Okay, now we just have to simplify that, so we get 12x minus 36 plus 4/3, which is 12x minus 104 divided by 3. Now we have this integral that we can do easily. So this is we are integrating with respect to x. So 12x, the integral of 12x would be 6x squared, and here we get 104 over 3 times x. Evaluated the upper limit, lower limit, and subtract. So we plug in 0, we're going to get 0. We plug in 2, we get 4 times 6, 24. Plug in 2 here, we get 208 over 3. And at the end, we get negative 136 over 3. Okay, so what I would like you to do is do this same problem where you're going to reverse the order of integration here. That is, instead of integrating with respect to y first, integrate with respect to x first. And when you do that, you should reverse the order of these two integral signs, and make sure, then you'll see that you get the same answer as I did. Here's another example. So if we have the double integral over r, actually, since it's already, we have spent 13 minutes, let me stop here and I'll do this example in the next video.